So good morning, everyone. I welcome you all to the third day of this STC on advances in high energy physics. And we are very fortunate today to have Professor Suchandra Dutta, Professor Saha Institute of Nuclear Physics with us today. Now I would like to request Mr. Shubham Sharma to start with the proceedings.
Hello, am I audible?
Yes, Shubham.
Okay. Professor Dutta has earned her PhD degree from Tata Institute of Fundamental Research and was postdoctoral fellow at Istituto Nazionale di Fisica Nucleare, Pisa, Italy, from 1997 to 2000, and she was research associate in the same institute from 2000 to 2005. From 2005 to 7, she has obtained her another postdoc from Scuola Normale Superiore, Pisa, Italy, and from 2009 to 10, she works as a research associate at University of Wisconsin and was associated to CMS Tracker Project, CERN, Geneva, Switzerland. From 2010 to 2011, she was postdoctoral fellow at National Center University, based at CERN, Taipei, Taiwan. From 2011 onwards, she has been serving Saha Institute of Nuclear Physics, Kolkatta. We are grateful to have you here, ma'am. On behalf of Organizing Committee, Physics Department and NIT Jalandhar, I welcome you, ma'am.
So now I would like to request Professor Suchandra Dutta to kindly take over and start interacting with our participants directly. Thank you, ma'am.
Sorry, ma'am, your microphone is in the mute position.
Good morning, ma'am. Good morning.
Good morning. I'm sorry. So thank you so much for inviting me to interact with you and talk about the tracking detectors. I will start my presentation now. I'll just basically switch off the video just to optimize the bandwidth I have. So let me just try to project. Is it visible?
Yes, ma'am.
Okay. So I'm going to discuss about the modern tracking detectors in the experimental high energy physics. So the outline of my talk will be the following. After a short introduction, I'll introduce tracking detectors. And nowadays, in the high energy physics experiment, the silicon tracking system is basically the baseline. So I'll spend basically a large fraction of my time with the silicon detectors. Then I will discuss when we start an experiment, what are the design considerations we have to take care of to design let's say plan for the detector. Then I will give examples of the tracking detectors in the LHC experiments, and I will focus mainly on the CMS tracking system as an use case, and I will show some of the performances of the sorry, I see the slides are not visible.
No, Suchandra, they are visible, I think. That might be a sort of individual problem on his behalf.
Okay, thank you. So I will show the performance of the CMS tracker as it is working now. So this will be basically my outline. So how do we track? Very, very simple starting point. We look for footprints. We try to correlate them. Then we join them together to find the direction, velocity, and in some cases also identification. But I want to stress here the identification is not easy. Just looking at the analogy, you see there is snow, and then a few people have walked through it. And from the footprints, we try to find out where, in which speed the track, the walking trail took place. So this is similar in the experiment. What we do here, we measure the charge particle trajectory. We call it a track. So I will mostly use tracking. So I just want to spell out the things to start with. We look for the direction and magnitude of its momentum. How do we do the tracking? When the charge particle crosses through a medium, it leaves trails in the medium, which we, in our case, it's a detector, which is basically active layers, and it leaves the trail due to its interaction with matter. Such trails are reconstructed as hits. So interaction of the particle in a medium, and we term it as a hit. It's a jargon in the experimental energy physics. Hits are then finally connected, and to connect them, it's called pattern recognition. How do we really connect the hits? To find out the trajectory of the charge particle, which is a track. And we also try to find out the point from where the tracks are originated. And that point is reconstructed as vertex. The word reconstructed means what we, let's take the example, like in the experiment, we have the collider experiment where collisions take place. After the collision, there are charged and neutral particles which are generated, and they basically move out from the interaction point. What we see in the detector are the footprints of those detectors, those charged particles. Then from those footprints, we reconstruct the trail or the track, and then we also go back to find out the origin of the track. So this point that we are going back, or from the hits we find out the trail, this terminology is called reconstruction. So throughout my my presentation, I will try to give you some idea about different types of tracking detectors. How do we track particles? How do we design the detector? What are the constraints or challenges we face when we design a detector? How do we overcome those challenges? And at the end, once we overcome the challenge, we design the detector, we build the detector, and then the detector performs, so the performance of the detector. So in this slide, I have shown in a very simple way how the in high energy physics, the detectors do perform. So we have different layers. You see in the right-hand side block diagram, there are different colors. So these are different types of detectors. First layer on the left is a blue region, which is the innermost layer, which is commonly we call the tracking detector, because the tracking detector is placed very close to the interaction point, because that's the point from where the charged particles and neutrals are generated. Then the red region is a calorimeter, where we measure the energy of the particle. Then there is a green region, which is also a calorimeter. What are the differences between red and green region? The red one is called electromagnetic calorimeter. The electromagnetic particles are measured there. And the green one is called hadron calorimeter, where we measure the hadrons. And then we have the muon system, because the muons are, they don't interact or interact very little with matter. And we try to trace the muons. So what I have tried to explain in the left are different types of particles. What happens? There could be a photon. The photon is chargeless, so photon will not give its footprints in the tracking detector. So if you can see, I don't know whether my mouse is visible. Is it visible?
Yes, maybe it is visible.
Okay. So when the photon, let's say, passes through these regions, what are its signatures? It will not give any track or any footprint in the tracking system. But in the electromagnetic calorimeter, it will shower and deposit its energy. So to identify a photon, we need a tracking system, although we don't have tracks there, but just to, let's say, confirm it's a photon, we need to know that there was no track. Instead, electron or a positron will give tracks in the tracking detector, and it will deposit its energy in the electromagnetic calorimeter. So you see, with the help of electromagnetic calorimeter and tracking detector, we can measure and identify photons and electrons. Muons, as I said before, they interact very little. They don't actually deposit their energy. They interact, they give footprints, but they don't deposit their energies. So you will see a track in the tracking detector. You will see very little energy deposits in the calorimeters, and it will pass through the last layer or last layers of the detector. And from this signature, we will identify it is a muon. So to identify muon, we need the tracking. We need electromagnetic and hadron calorimeter just to confirm that it's a muon. It didn't deposit that much energy. And we need the muon system. We can have charged hadrons. Let's say, common example, proton, pion. They will give, since it's a charged particle, it will give again the track. Then it will deposit some energy in the electromagnetic calorimeter and most of the energies in the hadron calorimeter. It will not go beyond the hadron calorimeter, and there will be nothing in the muon system. Similarly, neutral hadrons will not give any tracks, but it will deposit energy in the electromagnetic and hadron calorimeter. We can have neutrinos, which will be undetected because they don't interact at all, and we will not see the signatures. So we identify neutrino from the missing energy. So if we have, let's say, if we by some means we know the initial energy of the collision, then from the measurement of from all different detector systems, we know how much we could detect, and the one which we could not detect, undetected thing, we assign to neutrinos. So this is a very crude way. I mean, it's much more complicated, but it's a crude way to define how a high energy physics detector system works and what are the main ingredients of the detector system. Today in my lecture, I will concentrate on the innermost system, which is the tracking system. And you saw that it's not that we need the tracking system to detect a specific type of particle. Rather, tracking is the basic starting point of a high energy physics detector, because whether the particle is charged or the particle is neutral, we need the tracker. In charged case, it will confirm that it's a charged particle. It has gone through the detector. And in case of neutral, it will nullify. It will say that there was no footprints in the detector. And then from the calorimetric energy deposits, we will know that, okay, it's a neutral thing, either a photon or a neutral hadrons. So tracker is very important component of a modern detector system. How do we measure the tracks? In a homogeneous, we need to track charged particle. We need the active medium where the charged particle will interact. But we can have positive and negative charge. We want to also identify that, whether it's a positively charged particle, it's an electron or a positron. And also we need to measure the momentum. To do that, we need high magnetic field. Because in a magnetic field, the particle follows a circular path of radius r. Now, if you look at the left-hand side picture, you see that red lines are basically the layers of the detector system. So when I say tracker, in the previous picture, it was like a block, but in the block, there could be various layers so that we know the footprints at each layer, and due to the magnetic field, it will bend. Is it okay if I take the questions later on? Because if I have to check the chat box and...
No problem, ma'am. We will take the question at the end.
Okay, thank you. So it will interact at each layer of the tracking system, give the footprint, and from there we reconstruct the particle track. Now transverse momentum, which is perpendicular to the magnetic field, is related with the magnetic field and the radius of curvature. Like if a particle is very with very high momentum, then depending on the magnetic field, it will make the larger or smaller curvature. Okay, so we need to measure the curvature to know its momentum. So some mathematical expressions are given here, and you can see that the precision of measurement of the momentum of the charged particle comes from this sagitta measurement. So if this is my, this is the radius of curvature of the charged particle, and this tiny segment, which is denoted as S, the measurement precision depends on this tiny segment. And you can see that from this formula that depending on the PT, we will have the and also the magnetic field, we will have the curvature. So I give you a small example. So let's assume a magnetic field of 2 Tesla and a particle with PT 1 GeV. The radius of curvature will be 1 meter. Instead, if the PT is 10 GeV, the radius of curvature will be 16 centimeter. So, sorry, it should be meter. And if we consider a track length of 1 meter, the sagitta, the small s segment, can go from few centimeters to the millimeter. So if we want to measure a momentum with a precision of 10%, so let's say a PT is 10 GeV, we need to measure the sagitta in terms of 60 micron. So I just want to give you some quantitative argument here, that if we want to measure the momentum precisely, we need to measure the distance in a very precise manner. So this is how the detectors are designed, and you can see that when we have a low energy experiment, we have the charged particles with lower momentum, and we may not need very big tracking system to measure precisely its curvature, because low PT will make high curvature and we can easily measure the momentum. Instead, if we have very high momentum particles, we need large volume to have, because it will have a very large radius of curvature, and in that radius of curvature we have to measure this tiny distance to calculate its momentum. So these are the quantities which are defined to when we design a detector. So there are various types of detectors in the history of particle physics. We started with gaseous detectors, where the ionization of charged particle in the gas is measured, and from there the position and how much energy it released in the detector was measured. And the examples are multi-wire proportional chamber. I will not go into the details of the gaseous detector, but I just want to introduce. And the resolution, the measurement of position, I told you that is the most important quantity when we are talking about the tracking detector. And spatial resolution is defined by the spacing of the wires in the multi-wire proportional chamber. Sorry. There are also drift chambers, where we not only know it's again a gas detector, we can have some timing information which tells us when the particle crossed through and when the signal has reached the anode wire, and from there we know the time difference tells us the drift time between the primary ionization and the arrival of the signal in the anode wire, and from there we know precisely from which point the particle has crossed. So that gives us the position information. So drift chambers were very popular in the previous generation experiments. Oh, sorry. Then there are tracking detectors which give us also some identification information. One such detector is called transition radiation detector. What happens when the transition radiation is produced, when a ultra-relativistic charged particle traverses a medium with where the medium is not continuous. It has we have different mediums with different refractive indices, and let's say vacuum and dielectric layers. What happens? It emits the transition radiation. So again, from the deposited energy, the shape of the signal, we know that it was whether it was a heavier particle or a lighter particle, let's say electron. And transition radiation detectors are mostly used to identify electron positrons. And also its TRDs are heavily used also in the LHC experiments. Then there are time projection chamber, which is again a very novel idea, where it's kind of a drift chamber, but it has also, it can give us 3D coordinate measurement. So far we were discussing about 2D coordinates. This one can give us 3D coordinates. So we can have in one side wear chamber and the drip volume. So when the particle crosses through, we can get from the anode the position information from the XY plane, and Z coordinate can be taken from the wear chamber. So this is again used for the particle ID. It was used in the previous generation experiment like Aleph. Now it's used in Atlas. So now, why I said before that I will mostly spend time on the solid state detectors or the silicon detectors. The high energy physics in mid-70s, the new particles started to be discovered, and there were new quarks like C quark, B quark, and leptons, which had a lifetime which is of the order of 10 to the power minus 13 to 10 to the power minus 12, and it gives a decay length of 30 micron to 300 micron. So the tracking detectors were not, as I said also before, the tracking detectors are not only they not only measure the momentum of charge particle and the direction and the charge, but it also gives us some identification, which is important. And you can see the precision like 30 micron to 300 micron. So standard tracking detectors, basically the wear chambers, the drip chamber, time projection chamber, etc., they had the resolution of order of few hundred micron, and they became less sensitive to measure such distances. So a new tracking system with special resolution of few tens of microns became very important. So people started thinking about new technologies, and silicon came into picture at the time. And let's see the difference of characteristics between the gaseous detector and the solid state detectors. So what is silicon detector? It's array of silicon diodes used as a tracking medium. In comparison to the gas detector, where we have wares, and we had anode wares in between the cathode planes, charge particle crosses through, ionization is created and is collected in the anode. What happens in the solid state detector? We have a PN junction, and we deplete the bulk of the silicon. When the charge particle crosses through, it creates electron hole pairs, and then they are collected in the cathode strips. So in case of gas detectors, it's a volume of gas, and we have the wares. Here it's a solid state PN junction, and I will come to the description. Let's see the properties. In case of gaseous detector, we have basically, depending on the electric field which is applied, we can have a gain of 10 to the power 4. So if we have a charge particle cross through, depending on the electric field, we can amplify the ionization created. Instead, in case of solid state detectors, we don't have any amplification. We have ionization which is proportional to the thickness of the detector. The ionization energy to ionize gas molecules in case of gaseous detector is few tens of electron volts, whereas in the silicon detector it's few electron volt. You see the difference. Then we have the spatial resolution, which is order of few hundred micron, I already said, and here it is 10 to 50 micron, depends on the density of the material chosen. And the size, because in case of gas detector, we need a large volume, whereas the solid state detector could be very compact. So these are the advantages which came into picture, and the very good spatial resolution gave us the that basically dominated the usage of solid state device. Does it mean that we don't use gaseous detector? No, we do use gaseous detector, because I said before, very close to the interaction point, we need to have very good spatial resolution. But if we are far from the interaction point, when the tracks are well separated, we may not need that much spatial resolution. So gaseous detectors are still used in high energy physics, and they are mostly used in the outer part of the detector, which are the muon stations. So the working principle, I said, how does it work? We have a PN junction, P-type semiconductor, we have more holes, and N-type semiconductor, we have more free electron. Then if we have the junction, in the junction area, we have a depletion, and then it looks like a resistor, okay, because they start combining, and then we have this is the junction which is formed. Then we have like a resistor, so electron hole pairs which are created, but they recombine in the junction, and there are some free charges in the bulk area. And if we apply reverse bias, then it will be free from the pre-charge. So what happens if now a charge particle crosses through, it will create electron hole pairs, and then they will be collected with a very low ionization energy, and it has very large energy loss because it's a solid state device. We can have as large as 24K electron hole pairs. Let's say in a, this is wrong, it's a 300 micron silicon. So you see 300 micron is really a tiny thing. So it's a very good, it gives us very good position resolution, as well as it's very compact, and we can have a large signal. So that these properties played important role to select silicon devices as the tracking detector. How do they look like? So basically we have an N-type bulk. On top of that we have P strips. So it's a bulk, and on top of that there are, like in the gaseous detector we had wires, here we have the strips. And when the charge particle crosses through, the electron hole pairs are created, and then we collect them in the strips. Okay, and the position resolution depends by the distance between the strips, and we can have also different type, like instead of N-type bulk, we can have P-type bulk and N-type strip. This is something which will be used in the upgraded CMS tracker, which at the moment is being, let's say, being validated. The research and development is going on, and that has different reasons where we will, why we move away from N-type bulk to P-type bulk. But both options are possible. Now, signal. What is signal in a solid state detector? It's ionization produced in the depletion region. I said before, the energy loss is large due to this low ionization energy, and it basically shows a Landau distribution, the loss of the energy. and the mean energy per unit length, the most probable value is very, very low. And so another point to keep in mind, we in the very beginning, I showed that tracking detector is to trace the track of the charged particle. We don't want in the tracking detector the charged particle loses a lot of energy, because for that we have the calorimeter which are dedicated for the energy measurement. So the detector, when we design, we have to make sure that the energy loss in the detector is minimum. Okay, and the charge which is created, let's say the 24,000 electron volt pairs, we need to fully deplete the device. So we have to apply the voltage up to a level so that the detector is free of its majority carriers, because we don't want the charge, let's say electron hole pairs which are created due to the passage of the particle mix with the intrinsic electron, the space charge which are in the detector, and that's why we need to deplete it fully. The noise. So when we have signal, we also have noise. What are the sources of the noise? We have the leakage current. So although we have basically depleted the detector, there are minority carriers in the P or N-type silicon. So we have the reverse bias for the majority carriers, but for the minority carriers, this is the forward bias. So that gives us leakage current. So we need to have the material which is very pure, so that we can have as low as possible this leakage current. And it also depends, there is no direct temperature dependence, but I will come to that, why there is also a temperature dependence. There is also the noise coming from the capacitive coupling of the electronics, because we have the electronics which is connecting this the strips, and from there we have that is another source of noise. And we have also when we bias the detector, we have the resistors to bias it, and that is also another source of noise. So when we design the detector, we try to optimize its parameter, and you can see right hand side, bottom right hand side, there is a picture which is shown where the W by P is width over pitch. So pitch is the distance between the individual strips, and width is the width of the strip. So how the y-axis, it is the charge per centimeter. So the sorry, it's not the charge, the capacitive coupling which is created, which is proportional to the width over pitch. So we have to really design the detector in a way that if we keep the strips very close to each other, we will get very good position resolution. But if we keep the strips very close to each other, it will also increase the capacitive coupling. So there is some optimization which is performed before a detector is designed, because if we have a very high signal, we can afford to keep the noise at a manageable level. But if our signal is low, then of course we have to also minimize the noise. So this is a balance one has to take care of. So some characteristics. So just to show, the working point of a detector is defined by both signal and noise. So if we look at the most probable value of the signal as a function of the bias voltage, which is shown in the right hand side, you can so I said before, the signal gives a Landau shape. And if we take the most probable value of the Landau and we look as a function of the bias voltage, so you can see here the cards show at a very low bias voltage, let's say 50 to 100, the signal is increasing. Then we reach a point, from there the signal is flat. So this is how we define what should be the operating bias voltage of our detector. So we don't want to operate the detector in a region where it is not stable, it's increasing. So I told you before that we have the space charge, we apply the reverse bias, with the reverse bias, we remove the space charge and deplete the detector. And at some point when the detector is fully depleted, in this particular picture, let's say about 150 or so, from then on, even if we increase the bias voltage, the signal is flat because it's fully depleted. So whatever signal is collected from the detector is entirely coming from the charge particle which is passing through. And the noise is basically measured in terms of the fluctuation of the charge in absence of signal. So if we connect the electronics and we don't really allow any charge particle to cross through, we try to see what we read out in absence of external signal, and we check the fluctuation, and mean of this fluctuation is termed as noise, which is a measurement. And I showed before, there are different sources of noise, because when the detector is fully depleted and there is no external particle, we should, in case of ideal detector, we should have noise 0, but that's not 0. So that is the way we measure it, I mentioned. So signal over noise defines as the working point of a solid state detector. I will now go a little bit deeper in terms of the let's say it's not only the characteristics but the measurement of aspects. So if there are questions, maybe I can take a few questions before I move on, or it's okay if I take all questions at the end?
It totally depends on you whether you want to take questions now or later.
Sorry, can you speak louder? I could not hear you.
Yes, ma'am. It is totally dependent on you whether you want to take questions now or later. We are recording all the questions. We can ask them later or... Okay,
fine. Okay. So I discussed about the fact that we have, it's a very, very important, the spatial resolution, how we measure the footprint. Now, it depends on the fluctuation of the energy loss, because energy loss is not a fixed number. It's a Landau distribution, so it has a long tail due to the fluctuation. So this is the physical process, and also the diffusion of the charge, because the charge it's generated in the bulk and it has to move to the strip, so it diffuses while passing through. There are also external parameters. I said the strip pitch, the difference, the distance between the strips, the electronic noise, and also the sharing of charge between the neighboring strips. So we can have, in case of, let's say, 100 to 200 micron pitch detector, we can have 15 to 20 micron. 25 micron pitch gives us about 10 micron precision. Again, it depends on the experimental need, what is, how precisely we want to measure. And the design is considered accordingly. There is another, this is probably the most important aspect of a solid state device, that the impact of harsh radiation environment. The secondaries, let's say the PP collision, the secondaries which are created from the PP interaction and their products, or backscattered neutrons from the calorimeter, produce irreversible damage in silicon, which is not the case for the gaseous detector. So what happens? It increases the leakage current because the bulk of the silicon is damaged. It can, so when the leakage current increases, we need also higher depletion voltage to fully deplete the detector, and it also affects the spatial resolution. And there is some recovery. So when there is a damage, it can come back, which we call annealing process. It's a short-term annealing. So when the detector is damaged, there is a time period where part of it can come back, which is called annealing, and there is a irreversible damage, which is basically the long-term reverse annealing, which changes the depletion voltage. So all these substantially degrade the performance, affecting both aspects, the charge collection and spatial resolution. So to make a radiation resistant silicon, we need, there was a very, let's say, in the previous generation experiment, which was large electron positron collider, which worked up, at CERN up to year, I think 1999, and then on. Since 80s, the silicon detector started working in lab, but at the same time, a long-term research and development took place to find out the silicon which is really radiation resistant. For the considerations for the radiation resistant silicon is that we should have, it depends on the initial dopant concentration and resistivity, the crystal orientation, processing purity and quality, and also it requires low temperature operation. When a silicon is damaged, it has the high leakage current, I told you, but if we operate it at lower temperature, it can reduce the leakage current. It can control some of the reverse annealing, and it can also improve the charge collection, because when the device is damaged, there are trapping centers in the bulk. So when the charge particle crosses through, it creates electron hole pair, and the charge starts moving towards the strip, but due to these trapping centers, they get trapped. So we cannot collect the full charge which is created, and it lowers the signal. At the same time, it also increases the noise, which is due to the leakage current. So the performance is affected from both ends. The signal is reduced, the noise is increased, the signal over noise will be lower, and it requires very high voltage operation. And that is again can damage the detector. So this was the R&D to really create a very good silicon which can survive 10 years of LHC harsh condition, and which is proven now because LHC is already completed 10 years, and the detectors which were built, they are still working. Okay, there are damages, but it is there are also redundancies, so that the performance of the detector is unchanged. I said so much about the strip detectors. There are also pixel detectors, where the strip is not really a long strip along the bulk, but there are, as I have shown here, there are small rectangular implants which give us basically two-dimensional space point, very precise, depending on the size of these cells. These are called pixel detectors. They, in a very dense environment, strip detectors are not suitable. So I told you that silicon detector will be close to the interaction point, but very close to the interaction point, only strip detectors cannot give us the really cannot satisfy our need, and there the pixel detectors came into picture. So instead of strips, we have rectangular pixels, and they are highly segmented detector, and it helps for the pattern recognition, and it basically gives us three-dimensional points. And in the contrary of strip detectors, in pixel detector, the readout electronics is really coupled to the detector itself, that using a type of special type of connection. In case of strip, we have microstrip bonding, where the strip is connected to the electronics, whereas in case of pixel detector, we have the silicon sensor with this segmentation, and the readout chip is bonded on top of the detector. So the design considerations in the high energy physics experiment is, of course, the first and foremost point is the physics performance, heat resolution, primary and secondary vertex. I will come to that. What do I mean by primary and secondary vertices? There are also experiment-specific conditions, that what is the distance of the where exactly we can put the detector in with respect to the interaction point, what will be the track density, incident angle of the tracks, what will be the occupancy. Then I have a detector with, let's say, n number of channels, and what are occupancy means how many out of those channels are fired. Strip pitch and separation, I told you before, the number of readout channel, the trigger rate, available time for the signal processing, the size of the data we can handle. Also, it depends on the best available industrial facility, because we depend entirely on the industry to have better and better materials. So, and I mean, there are also, let's say, innovative ideas in the industry, which we basically go hand in hand, the industry and research. Mechanical constraint, considering the overall detector design, efficient cooling, and as light as possible for efficient tracking, and of course the cost, because we can increase as many as in the design, we can increase the number of channels, because we want to measure the positions very precisely. But once we increase the number of channels, we have other consequences, and of course there is cost. So a balance is drawn between all these facts to design the detector, but mostly it's experiment specific, but in almost all cases, we have a few layers of pixel detectors very close to the interaction point, and followed by layers of strip detectors. Now I move to LHC and specific cases where these detectors are used. So here I give one physics example. You heard about the standard model from Rohini yesterday. So let's say a process in standard model where Higgs goes to ZZ, and it gives us 2 muons, 2 electrons. The top picture it shows, it's of course simulation, it's not real data. There are nothing else in during this collision. So you will see the deposit of energy in the electromagnetic calorimeter and muon tracks, 2 muon tracks. Very easy, one can reconstruct. Okay, this is, you measure the momentum energy deposit, and from there you can find out that it came from Higgs events. It's not so easy in case of LHC, because when the collisions are taking place, depending on the luminosity is how much collisions we are, because in case of what we are trying to, I think you have also heard from Kajari that we are looking for something new, and this something new is the signal from something new is very little compared to something which we know very well. That's why what we try to do is to make many collisions, so that we have a lot of data, and from there we try to find out the interesting events. So this is in some, I mean, I'm telling you in a crude way because I don't want to go into the details. So depending on the luminosity, which measures how much collisions are taking place, we can have a given collision superimposed with some pile-up events. Pile-up is other PP collisions which are superimposed when we are having the real collision. So if here in the example, you can see that the same Higgs going to 2 mu 2 electron event is superimposed with only 2 pile-up events and with 20 pile-up events. So you can see the detector has to really find out from this derby of junks those 4 useful information. So it's basically thousands of charged particles which are coming out from the interaction point, and from there we have to find out our interesting event. So this imposes stringent condition on the detector system. So what are those stringent conditions? High energy collisions, these are the energies are very high. I told you that when there is very high energy, we need to, the curvature will be smaller. We need a larger volume, and with high luminosity, it's very high rate. So in a given, so it's a 25 nanosecond bunch crossing. So collisions are taking place 10 to the power, in a, let's say in terms of nanosecond is 10 to the power minus 9 second. Okay, so it's the difference between one collision and another is 25 nanoseconds. So it's very fast. High particle density, very large number of particles, which if you really want to separate out, you need to make the detector granular enough, highly segmented detectors, and high radiation. So radiation due to particles from collision, radiation imposes. I already spent a lot of time on the radiation resistant things, because once we install a detector, we really cannot change it. We have to work with it for tens of years. So how do we face the challenge? We measure the particle track in various points, which we call the hits. We need a very strong magnetic field to because with a higher magnetic field, it will bend more, and we can measure the momentum precisely. it has a very high occupancy. Occupancy means, as I said, in a given detector, I have channels, and in a given collision, if all my channels are, let's say, fired, then I will not be able to separate out this collision from the next one. So we have to make the occupancy low in a detector. That means we have very highly segmented detector. But if we increase the granularity to reduce the occupancy, it will also increase the electronic channel, and it will also have higher heat load. So it will need cooling. Radiation environment has its requirement on the signal and noise, because we need signal and noise at a reasonable level to add it for the to measure it properly. And also we have to minimize the material so that the when the particle is going to the calorimeter, it should not lose all its energy in the tracker, because tracker is just for the momentum measurement and the energy is measured in the calorimeter. So the material of the tracking volume should be as low as possible. We need a very fast electronic system. As I said, that each collision is taking place at 25 nanoseconds. So the detector should be fast enough. We need to extrapolate the tracks. Once the tracks are reconstructed, we need to extrapolate the tracks to find the origin of the tracks. So this is we call it a primary vertex from where it is generated, and we need also to identify secondary vertex. What is secondary vertex? That when a particle is generated from the interaction, and during its flight path, if it decays, then it creates secondaries. So we want to find out that particular point from where the decay occurred, because then from its property, we will know which type of particle it is, whether it's a tau lepton, a B quark, or C. Okay, and the tracker also, depending on the experiment, can have some identification of particles, like energy loss per unit length. This is a way to know the particle type, and also there are different types of detectors to have the particle identification. Again, this is experiment specific. I give you a few examples. So it's ALICE, which is an experiment where the heavy ion collision is recorded, and in the ALICE detector we have the silicon pixel detector at the core. Sorry, the color coding here and here are different, just ignore. So in very close to the interaction point, it's a pixel detector. Then there is silicon drip detector. It's a very innovative detector. It's not gaseous drip detector, it's a silicon drip detector. And there are silicon strip detector. So these three layers in the inner part of the tracking system. Then they have in the picture right hand side below, you see this blue region, which is a time projection chamber, and they have the transition radiation detector. So ALICE tracking system is really innovative, and they have different types of detectors. Combining all types of detectors, one can measure the momentum of the charged particle as well as the type of the charged particle. ATLAS is another experiment where generic PP physics is studied, like CMS. They have transition radiation detector at the outer part of the tracking system. They have silicon strip detector in the inner part, and they have the pixel detector. And if you can read the numbers, the first layer of pixel detector is at 33 millimeter with respect to the interaction point. Just to give you some idea of, like where exactly we are measuring, and the tracking system really extends from 33 millimeter up to let's say 1 meter. So you can imagine the size of the system. Now let me come to the CMS experiment. I'll spend some time there. So it is the largest silicon tracker ever built. So in case of CMS, it's a fully silicon tracker. We don't have any other type of detector in the tracking system. It has 240 meter square of active silicon, and it is 5 meter long and 2.5 meter in diameter. This is a huge tracker made of silicon. It has strip and pixel detector. Again, in very core of the detector, which is shown in this purple color, is pixel detector, and then there are silicon strip detector. We have, let's say, in the if we consider the number of measurement points, it is from 13 onwards, let's say 13 to I think it's up to 25 measurement points to ensure the redundancy in tracking. I told before that due to radiation, there are damages in the detector because we are running, let's say, already more than 10 years. So there are damages. So some detectors get, and this is also very well monitored, the damages. And if a detector doesn't work, since we have the redundancy, a large number of measurement points, which are very precise, even if we miss 1 or 2 points, we can the performance is not affected. Some specifications of the detector. We have the individual detector dimensions are given here. The pitch, which I discussed before, these are for the strip detectors, is from 80 micron to 120 micron. And in the outer part, as I said, that when we are closer to the interaction point, we need to measure things because the tracks are very dense there. So we need much more, let's say, precision, or let's say more granular detectors there. We go outward from the interaction point, we can afford having less granularity. So you see the inner part has 80 to 120 micron, outer part is 180, it can go up to 180. It is produced from 6-inch silicon wafer, because when we are defining a detector, the detector dimensions, it depends directly on the industrial production line. Because if we can align ourselves towards the industrial production line, the detector will be cheaper, because industry will not define a production line for the experiment. Industry has its own production line. We have to align ourselves. So we could use detectors from 6-inch wafer, and we have 2 types of silicon detectors in the strip detectors. The inner part has 300 micron silicon, outer part has 500 micron silicon. I will just spend, I think, 1 slide here, that when CMS decided to use only gaseous detector, it was, let's say, it is again a big step forward, because at that time we decided to really cover the full detector with silicon, I mean full tracker with silicon, and with 300 micron silicon it was not possible, because outer layers we wanted to use bigger detector, and with very thin silicon it was difficult to handle, so we wanted to increase the thickness. Now to have the thicker detector, this is the first time in CMS we used 500 micron, and a lot of R&D took place, and we verified that when we increase the thickness, we have larger signal, because when we increase the detector size, the strip is also increased, and it increased the source of the noise. So if we don't increase the signal, then again signal over noise will be lower. So this was, I show this slide just to make, just to let you know that this was again a big step forward to use thicker silicon in the high energy physics experiment, which was done in CMS. A few pictures just to show how they look like. These are mostly for the strip detectors. You can see these are the individual building blocks, different shape and size depending on where in the geometry they are located. These are the readout electronics, and the strips are here they are connected to the readout electronics with the microstrip bonding. And once from those building blocks, we have again some, let's say, substructures where those building blocks are put together. Then those building blocks are joined together, and this is a cross-sectional view of the silicon strip tracker, which is really unique. Of it has 15,000 silicon strip small detectors, the ones which I showed before. It has 10 million strips and 80,000 electronic chips. It's the detector, I mean, it doesn't come of its own. It has also the cables, connectors. You see the 40,000 optical fibers to carry the signals at 100 meter distance from the detector, where we have the readout modules. And this is another size, thousands of fibers, and they are connections, like these fibers are connected to individual small detector units, and we have to really label them properly, so that finally when we collect the signal from these thousands of channels, we have to make sure from exactly from where they are coming from. So all these things are nicely included in a database which is used when we process the signal. And finally, the detector, the tracker was inserted in the full CMS detector. So this is the whole tracker being inserted. A few slides now, just to show the performances. I told so many times the heat, position, resolution, etc. What happens? We have a charge particle crossing through. It gives signal. In the yellow line, I am showing the signals, and from there we construct the heat, because we can have more than one particle crossing through. We can have noise. So what happens? We check the position with some clustering of signals. So we apply a particular threshold to find out the largest signal. Then we look for nearby signals, and then we collect the signals if it crosses another threshold, and then we combine them, and we get we apply the third threshold to call, okay, it is coming from a particle. So this is defined as heat, and this is how the heat is reconstructed. And if we look at the occupancy, I discussed before that we don't, I mean, we have thousands of strips in this small detector unit, and we want to make sure that the occupancy should be very low. Now, if we go away from the interaction point, of course, the occupancy is low, but very close to the interaction point, let's say 25 centimeter, we have 0.03, which is it is basically of 1000. And if we go outwards from the, I think this is for the pixels. It is here a multiplication of 10 to the power minus 4 is there. So in case of pixels, the occupancy is even lower. Okay. Then position resolution, I told you the heat. So how precisely we can measure the heat? So you can see in this table I have shown the pitch. Pitch is, again, just to remind, the difference between the position difference between two strips. So if the pitch is 80 micron, we have, these are basically the specifications in different parts of the tracker. So these are the, let's say if we check the pitch, which is 80 micron, the resolution here is, let's say 20 micron, even lower. And then when the pitch is increased, you see the resolution is also increased. But anyway, we have everything below 50 micron. This is for the strip detector. Pixel is even better because we need better precision there. Once we define the hits, we now need to reconstruct the track or the trace of the particle. So what happens? I try to show it from this picture. So we have a hit in a given, these are the layers of the tracker. So we have a hit here. Then we want to know, we define a track segment from the inner part, and then we propagate that segment to find out the hits. And to do that, we basically iteratively collect the hits. So let's say we have, this is the initial hit segment, and then there is some material. We have the multiple scattering, and we define the opening angle depending on the multiple scattering, and then we collect the hits from the next layer and next, so on. This is how we move forward. I give you, try to explain it from another cartoon. So in case of CMS, we have the pixel layers in the innermost part, and the initial segment, which is called a seed, is created from the hits in the pixel. Okay, those are very precise hits. And then once we create these track segments or seed, we try to do the pattern recognition, and we basically move forward to collect the hits from the other layers. And this is an iterative process. It's called pattern recognition. When we are satisfied with the pattern recognition, we fit the track, and we go on doing, I have shown it in a few lines, but it is much more complicated. I just do not want to go into the details. And while doing that, we have to also consider the condition of the tracker, which is called tracker calibration. When we are saying that we collect a hit, we have to know whether the channel of that detector is good. So we need to calibrate the detector to find out bad channels. We try to find out what is the Lorentz angle. We try to see whether we need to increase the bias voltage, because with the bias voltage, we have the signal, we need to go into the, let's say, uniform region of the signal. We don't, so with radiation, the bias voltage, the operating bias voltage can also change. So we have to monitor that. We have to check the gain of the laser drivers, because we are collecting the signal optically. We check the pedestal and the noise measurement throughout the data taking period. And you can see here the bad channels as a function of, let's say, the collected luminosity in different years of data taking. They are stable. There are sometimes there are bad strips. We have to really discard those strips to find out when we define the heat. Otherwise, we will not be able to really measure the momentum correctly. Just one picture to show that this is the resolution of momentum. So the momentum measurement, let's say in the central part of the detector, in blue, it is coming from muon system only. In green, it is from the tracker system. And in red, if we combine the two. So you can see up to, and in x-axis, it is the momentum of the track, and y-axis is the measurement precision or the resolution. And you can see the size of the CMS tracker and the magnetic field allows us to measure the track very precisely up to say few hundred GV tracks. If the track is track PT is much more than that, then it is the muon system which can measure it better than tracker. And if we combine the two, because in case of tracker the measurement error increases. So if we combine the two, we can, with the red line, you can see that up to few TVs, we can measure the track within few percent errors, track PT. In tracking, another important aspect is alignment, that when we are measuring the track, we want to make sure that the detector is aligned properly. What can happen is, take a picture like this. We have few layers of the detector, a real track passes through, it produces hits in each detector. But this particular detector, the third one, is displaced from its position. By displaced here, I mean a few microns. It can happen due to mechanical issues, the temperature effect, anything, okay? Now, if we now try to reconstruct the track, without knowing that this detector is not in its nominal position, what happens? We will reconstruct the track assuming that because when we are measuring the hits, we measure in the detector itself, in its local system. So since the hit is here, we assume that the detector was in its normal position and heat will be here, okay? And then we reconstruct the track like that. But if we do alignment, means if we reconstruct the track like that, we have the distance of the reconstructed track from this particular heat is large, which will make the track PT measurement wrong. So what we have to do, we have to align the detector to have its original position, because here we assumed, but this is not the case. Actually, the detector is moved. If you take that into account, then we should be able to reconstruct the track as it has passed through. So we need really to align the detector. And I just show you, let's say, the measurement here in the top left picture. I'm showing the residual, which is the track, the difference, the distance of the track with reconstructed track with respect to the measured heat. If we don't do any alignment, this is the red line. If we do the alignment, then we have this blue region, which gives us very good precision. So this is something which we measure every time we take data. And you see here again, as a function of phi, the measurement, the red one before we do any alignment, and the blue one when we have done a very good alignment. Once all these things are done correctly, we can measure the track properties. So here I'm showing as a function of the momentum of muon, at which efficiency we can measure the track. At which efficiency we can measure the track as a function of, let's say, position of the track in the detector, or as a function of number of primary vertices in the event, because I told you there are more than one collision which is happening, and out of that we have one, let's say, the interesting collision. And you can see that it is really efficient whether we are having a track up to, let's say, 200 GV, we have 100% efficiency also in different geometric region, and as a function of how many interactions took place. So vertex resolution, vertex reconstruction, very quickly, we have we try to find out where exactly the tracks originate from. So this is called, so if we reconstruct the tracks, the red and blue lines, we trace them back to find out the point from where they have originated. This helps us to find out the interesting primary vertex and the pile-up vertex, which are coming from superimposed collisions which are taking place. We also measure the secondary vertex to identify particles. I told you the hadrons, where we have a B quark or a C quark, or even a lepton, which is tau lepton, which decays on the fly when it reaches the detector. Okay, so here I'm showing the primary vertex once it is reconstructed. You see, the scale is millimeter. This is 1 millimeter, and you can see how well the interaction primary vertex is reconstructed. And if we calculate the error in the vertex measurement, how it goes as a function of track PT, it's in terms of millimeters. So this is the beauty of silicon detector, that you can really measure things in terms of few tens of microns precision. I will just stop here showing a picture where I have shown the fact that the compact muon solenoid justifies its name, because you see here, if we try to measure the invariant mass from two muon system, so nicely all the particles which were discovered in previous generation experiments are nicely reconstructed. And this is basically, as I said, this is muon, so it is the beauty of silicon, CMS silicon strip tracker, and the very good muon system, which I didn't cover in my lecture today. That's all from my side.
Thank you so much, ma'am. Ma'am, we have some questions with you. Can I ask?
Yes.
There's a question from Saddam Salman that will it be possible to track particle detectors between the point of collision and the point it reaches the innermost layer?
Point of collision and no.
Collision to the innermost layer.
No, it's not. It's not really a track. Instead, it is basically what happens. I think I showed here. Actually, we have nothing in between, right? We have the beam pipe. Let me see if I have a picture of that. So the question is, let's say the collision is taking place in this beam pipe, and I have first detector at let's say 33 millimeter. We cannot measure anything from 0 to 33, but if we can measure what happened in from 33 to 1 meter, we can extrapolate back and find out where exactly the collision took place. That's how the primary vertex is reconstructed. Is that answer your question?
Yes, ma'am. And the second question is, muon is considered heavy as a heavier counterpart of electron, and why the electron deposit energy in the innermost layer of tracking detector, but muon does not.
It depends on the nature of the particle. So, okay, the energy loss of electron in the tracker and the energy loss of muon in the tracker are similar. But in case of not similar, depends also on the mass. Muon is heavier. But electron has other processes like bremsstrahlung, where when it is crosses through the medium, it can emit a photon. Then the photon can make pair production. And this bremsstrahlung process is basically proportional, inversely proportional to the mass. So in case of electron, it's much more with respect to muon because of its mass. So in case of electron, we try to minimize the material in the tracker so that the energy loss of charged particle in the tracker is as low as possible. But we want electron to make the energy loss in the electromagnetic calorimeter because we want to measure it. And I think Shattuku will cover what happens in the calorimeter today. So it's a combination of bremsstrahlung and pair production which happens in the calorimeter by electron and positron, and it loses all its energy. Muon doesn't, because it does very little interaction with the matter. It can ionize, but it doesn't lose its energy. And that's how it can pass through, and this is the signature from which we identify muons.
Okay, thank you, ma'am. Ma'am, the another question is, we know that uncertainty principle is involved. We cannot measure momentum and position at the same time. While we are measuring the position, is uncertainty principle is followed, or what kind of uncertainty we have in our data? Uncertainty or discrepancy?
I mean, the discrepancy is something which I showed. When we measure with a precision. We don't measure things which is absolute. It depends. Like that's why it's called the resolution. The resolution is basically estimate of measurement error. I think I could not really answer the question.
Okay, ma'am, got it. Now, there is one question related to noise. How electronic noise in the detector systems can be eliminated or minimized?
Okay, it's a very good question. I mean, we really cannot eliminate the noise. We can try to minimize it from the sources. As I said, that in case of, I mean, for example, for the pixel detector, we have a really very low noise. But in case of strip detector, we have higher noise. So it depends on the geometry, the choice of the material, and also the electronics. So if we have the analog electronics, it has its intrinsic noise. If we use a digital electronics, we minimize the noise, but at the same time, we really cannot measure the signal. It will be like, as its name, it will say yes or no, whether there was a signal or no signal. But how much signal, it's not cannot be measured. So it again, it's a let's say balance between the need and the available options. For example, in case of CMS, we have the analog readout in for the and digital readout in case of pixel detector.
Okay, ma'am. Ma'am, how are photons or gamma rays produced in the decay of Higgs is isolated from pile of final states?
No, I could not understand the question. Can you repeat?
There is a question from Ruchi Sharma. She said how the photons and gamma rays, which are produced in the decay of Higgs, are isolated from the pile of final states.
how they are
Means how the
isolated.
tone and gamma ray peaks are, filtered out, and we can only see the final result. I think she wanna ask something like that.
It's not really isolated. It's a very complex procedure. I really cannot explain it in few words, but it's not. I mean, I don't know whether you have seen the pictures of two photon peak in the Higgs analysis. It's really tiny peak on top of a huge background, because these two photons can come from also if there is a pi zero, it can give you two photons. But in case of Higgs, it is let's say the photons which are emitted are high energetic. Then there are a lot of let's say analysis steps to make sure that these are really pure photon coming from Higgs. It's really difficult for me to explain without the material here. I'm not prepared for that. But it's really a very good question.
Okay, thank you, ma'am. That's all with the questions, and thank you so much for this informative talk.
Okay, thank you to all.
Thank you so much, ma'am, for joining.
Thanks a lot, Suchandra ji, for.
Thanks a lot for giving me this opportunity. It was very nice. Bye.
Bye, ma'am. Bye. Thank you.